Yeah, good afternoon, everyone. It is my pleasure to introduce Sunny Jung from Cornell University. He's our MC lecturer. He's here. He's giving talk in Newcastle. I think he's heading to Western Australia.
Yeah.
Tomorrow.
Yeah.
He's talking about transport mechanisms induced by raindrop impact. Really applied talks, please.
All right. Thank you. Yes, so it's a great pleasure to be University of Newcastle. It's the first time to visit here. It's beautiful the place. I just walk around the beach. The hotel was really good. The Noah on the beach. It's really good. So I will talk about the transport mechanism. So my background is in physics, even though I was postdoc and instructor in applied math, but the basic training was physics. So what I usually do, I try to either make observations in nature and develop the theoretical model and then solve this model and try to understand why nature behaves like this. So that's the sort of theme what I'm doing here. So I'm trying to explain about the raindrop impact. So this is an instant drop impact on the insects. And then we try to understand how insects evolve in a way that you have a certain surface structure to break this raindrop apart. So that's the topic I'm going to talk about. So in nature, there are a lot of the rains falling. So it's very dangerous for especially small insects or animals. So this is hummingbird, but I couldn't find a good video of the insects impact by the raindrops. But in general, like insects or butterfly, it's about like 100 to 500 milligrams. By weight. Maybe I should understand. Okay. Anyway, and then raindrop by itself is about it's about 30 to 50 milligrams. So it's about like a 1/10 of the body weight of the drop impacting on the insects. So this is similar to the bowling balls falling at you, to the human. So how dangerous it is. So a very dangerous process. So the physics tell us when drop or any two objects in contact, there are three things can be transported between those two objects. So first one is mass transfer. So which is when let's say raindrop impact on the surface and some of the drops can be left on the surface. So there can be some like a mass transfer between the two objects. Second thing is a momentum transfer. When this the raindrop impact on the flexible surface, then you're gonna see the bending or the change, the velocity of the impacted the surface too. Third one is the heat transfer. So some of the heat can be transferred if the raindrop is cold enough, then there can be some heat transfer between the object and the raindrop. That's why when you walk in the rain, you lose your body temperature, right? So all these three transport mechanism depends on the contact time. So one of the strategy maybe nature can develop is they want to reduce the contact time when they fly or when they walk in the rain. So there's I'm trying to explore the first topic. So the engineers try to develop this kind of the special surface to reduce contact time because there are a lot of application in terms of heat transfer. A lot of the big plant, the heat is one of the biggest the quantity they need to optimize. So when you have a super hydrophobic surface is a surface repel the water. So like typical leaves out there, if you put the water drop, then you're gonna see water does not wet. We're just sitting on the leaf as a spherical shape. So it's a super hydrophobic surface. With the raindrop impact, then you're gonna see it spread and retract by the surface tension. It just bounce off. The other study people look at is what if you have a line structure, then this impacted raindrop or drop will break into the pieces, and they're going to reduce the contact time, which is almost like I think about 30% decrease in the contact time. And when you have a very like a high aspect ratio needle-like structure, then you can further decrease the contact time by 3 milliseconds, which is a very short time in contact. So previous study, they look at the very gentle water drop impact. So speed is around 1 to 3 meters per second. However, in the actual rain, what we are seeing outside, the speed of the raindrop is between the 2 to 15 meters per second, which is quite high compared to what people studied. So one of the things we try to look at is what really happened with a really high speed raindrop impact on the superhydrophobic surface. So that is sort of the goal of this first part of my talk. So we try to test many natural surfaces, the bird wing and dragonfly, and then I think this is a butterfly, and these are the moth, and also plant leaf too. And all these surfaces are superhydrophobic, which has contact angle, which is 120, means if you put the drop on the surface, you're gonna make a more almost like spherical shape of the drop on the surface. And if you look at the more carefully on the microscopic structure, all these structures has a little roughness because due to the scale, or some of the these kind of insect wings, they have a little like sensors, hairs sticking out. And also leaves are not smooth, it has a little bumpy structure. So we also make an engineering surface to mimic this kind of superhydrophobic surface. So we make a little pillar structure on the surface. So we can test all these 7 different surfaces with the impact. So this is one of the high-speed video of the raindrop impact on the bird feather. And this is you see insect wing and also the leaf surface. One thing you're gonna see is you're gonna see very high-speed spreading happens. And after spread, it never really coalesces much. So just a spread, and then it breaks into the small pieces. So this is something interesting we try to look at more carefully. So there's no smooth bouncing. And also there's a lot of the interesting, the V-shape like a structure form when this the drop is spreading on this rough surface. So this is the first one, is the relatively low speed impact in our lab, what we did. So you're gonna see nice spreading and it bounce off from the surface. Let's see what happened if I put the So if you have about 4 meters per second, then you're gonna see quite different behavior. Spread, it never coalesce, just scatter into the small pieces. So we try to understand these kind of dynamics here. So definitely it reduces the contact time. So we look at the microscope lens and we try to see how the fluid will spread. So impact happens on the far left here. And this is about like a 1200 micrometers. So overall, this is only 1 millimeter. So you're gonna see very microscopic the structure in this video. And I will mask out the little bumpy structure here. And you're gonna see how fluid will be spread on top of this structure. So there are a couple of things you're gonna see. First, you're gonna see the wavy surface form due to this kind of the microstructures inside. And other thing is you're gonna see the reducing the thickness of film, which makes sense because once drop impact, it will spread, and then as you increase the area, you will reduce the thickness. And the third thing is at a certain point right here, this top of this the hydrophobic surface touches the interface, and it will pop. So it's kind of popping happens. So we're gonna see this kind of popping behavior on the top-down view. So you're gonna see at the location of the microbump, you're gonna see the whole nucleation. So sort of it nucleate the small air pockets in the thin film. So what we are trying to understand is when this lower part of the upper interface touch the top of this bump. So that is sort of the geometric threshold we're gonna look for from the theoretical model in the next page. So this geometric model, so we're gonna look at the continuity, which is how the film get thinner as it spread out, radially out. And we use the Euler equation which is we ignore this viscous term. We take into account only the capillary surface tension force, which is depends on the curvature of this interface, upper interface. And then we assume the H follow the R cubed divided by UT squared, which is this expression is coming from it's called the Savart sheet. When you shoot the jet on any object, you will make a nice sheet of the liquid film. So and they measure the thickness of the liquid film in the Savart sheet. So this is following this expression. So we're gonna approximate the lower is a bumpy structure as a sinusoidal function here, and we try to see how this surface wave will retract and how surface wave decrease the thickness and how what kind of amplitude the surface wave will have. So we use the dynamic and kinematic bounding condition. So dynamic bounding condition based on the surface tension, and kinetic bounding condition is coming from the vertical velocity as depends on the height, eta change times the u, the horizontal velocity times the gradient of this height. And we assume the velocity potential as a sine and exponential function, which is coming from the Laplace equation of the velocity potential. And if you combine all of this, then you're gonna get the simple relation, which is when this the hole will nucleate, which is goes like an epsilon. Epsilon is the height of this bump, and then -1/2 power, and r is the radius of drop, and u is the speed of impact. So we're gonna just try to check whether this is correct. So we ran a lot of experiments. We tested on the artificial surface and dragonfly and the moth and the feathers. And then when we rescale this one based on our theoretical prediction on the x-axis, we can collect this data quite well, which means the whole nucleate at the time scale following this prediction, which is it can express as the square root of the ratio of the radius of drop and the size of bump, and then R over U is the inertial time scale. Furthermore, we also predict what is the critical velocity to create the nucleate, to create the nucleation, whole nucleation here. So we tested many different samples here, and then we find the critical velocity, and they are following the nice relation is as function of the epsilon. Epsilon is the size of the bump structure, and you can see it follows the prediction what we have here, which is a critical velocity scale as the square root of 1/epsilon, which is nice relation. So I will switch to the next topic. So one I showed you earlier is how the animals or insects have a rough structure to scatter the impacting raindrop. So next topic is about the momentum transfer and also mass transfer. So when the drop impact on the flexible leaf, so this is the wheat. So you can see the wheat head on the background, and this is a wheat leaf. So when this raindrop impact on the flexible the leaf, and the leaf will start to flutter, and as it flutters, it will create the spreading of the particles around. So these particles can be spores, and that's the biggest problem in the agriculture. I will explain in a minute. So the spore spreading in the agriculture can damage the crop yield. So why I'm interested in the raindrop impact on the leaf? Well, first of all, not many people study this kind of area, and the reason I'm interested due to the basic physics. So this is a stress-time relation, which is suggested by the Carl Nicholas in his book. So in general, like if you have if you look at the life of the plant, there are a lot of different levels of stress the plant experience. Especially the one we have a high stress will have a short duration. Let's say raindrop impact once the raindrop impact, and they will stick on the leaf only like a fraction of a second, and it will just scatter around. So it's about like this. And over the minutes of the hours, so wind is keep blowing, so then leaf is get stressed. And over days, if you have snow, then the plant will experience the stress by having the snow on the leaf, and the gravity can keep acting on the plant over years. So this is something interesting, and especially I'm interested in the very high stress case, which is a raindrop. So that's why I'm interested. So this is a stress on the plant, which is true for stress on humans too. So daily life is very stressful, and graduating college and buying house, and at the end, life is good. Right? There's a singularity. So when you are tenure track, you need to get a tenure, or you need to do the final defense. And there's another singularity, and this origin, which is my 1 hour seminar might be stressful for you. So my goal is I'm trying to reduce your stress as much as possible. So the Charles Chaplin said, like, life is tragedy when seen in close up, but a comedy in long shot. So same as a plant. So I will take a look at the plant tragedy, the raindrop impact on the plant. So as I mentioned briefly, the spore is very important in agriculture in general. And there's a healthy, the wheat leaf is a very green. But once it's impacted by the spores, then you're going to see this kind of orange spots appears on the leaf. And if you look at it closely, you will have a bunch of like 100 or thousands of the spores is emerging from the skin of the leaf. So impaction happens inside the leaf. And each spore is about 100 micrometer in radius. And one of the interesting facts is these spores can get up to the atmosphere, like a few kilometers high up in the air, and it cross the continent. So due to the Coriolis force driven the atmospheric flow, can some of the spores can go to the Europe, and some spores from Europe get into Australia, and vice versa. So there are a lot of exchange of spores. That can be the biggest problem across the world here. So one of the interesting fact people find out, there are a lot of spores get up in the air just after rain. So this blue dot is a rain precipitation, and you'll see the yellow spike, which is the highest bioparticles in the air. So you're gonna see this kind of spike happens just after rainfall. You might have experienced this one when you walk outside during the rain. So you're gonna, in the beginning of the rain, you're gonna smell the soil, right? So you're gonna smell a little bit of the dust, right? So due to the rain is falling down, this due to the inertia of the raindrop will create a lot of the spores or the particles up in the air. So that's why you can smell this kind of the spore, the particles during the beginning of the rain. So this is what we did experiment with in collaboration with the plant pathologists. So they make a lot of the wheat is infected, and after raindrop impact, you're gonna see a lot of the black dust. Those are all the spores. And this is on the bottom of the petri dish. You can see a lot of spores ejected. And I have undergraduate students just count all the spores manually. So about 1,000 and 3,000 and 4,000, 5,000. So depending on the impact speed of the raindrop, you can see a lot of the spores can. So a single raindrop can create 1,000 spores up in the air and then just sediment on the ground. So first we look at the mechanism why there are a lot of the spores get up in the air even with a single raindrop impact. So the raindrop is around like a few millimeters in radius. So if I count how many spores under this kind of area, it's only like a less than 1,000. But somehow we got more than the 1,000 spores ejected by the raindrop impact. what we find out, the interesting phenomena, we shine the laser sheet at the moment of the location of the raindrop. And when the raindrop impact, so what happened is it carries a lot of momentum with it and suddenly stop. And then what happened? It creates the vortex ring. So ring of vortex is connected in this kind of shape. And this vortex ring will scavenge a lot of the spores on the surface up in the air. This is the one thing we find in this paper. So we just look at the circulation and other stuff. Okay, so that's what we have studied, and then we try to look at the elasticity of the leaf. So what I showed you earlier is the fixed leaf. Then we try to look at the elasticity. So what happens is that what we expect when the raindrop impact on the leaf, then the leaf start to flutter, and then it can eject a lot of the spores up in the air. So we try to visualize what kind of flow field it generates when the leaf is fluttering. So what you are seeing in this video, you are looking from the top. So leaf is elongated in this direction, is fluttering this up and down. And you're gonna see a nice vortex shedded on the edge of the leaf. So you can just calculate what is the circulation or what is the vortices generated from the edge of the leaf. So to quantify this one, we use the 2D complex velocity potential, which is introduced by the Wegener and the von Karman. So this velocity potential, and plus we also look at the momentum balance, how much the momentum this raindrop carries to how much the leaf will what is the velocity or momentum balance. What is the momentum induced by the raindrop impact? So this is what we can calculate here. And from those two, we can calculate the circulation, which is the vortices integrate over the certain area, which is simply depends on the dc dt, which is the velocity, vertical velocity of the beam. And you can see here, so this is theoretical line, and that is from the experiment, and can follow what we are observing in this experiment too. So then we did experiment, we put some particles on the leaf, and then we just release the raindrop, and you're gonna see a nice swirling or vortices shedded from the side. And we try to understand where these particles go. So one of the analysis we're going to use is called the backward finite time Lyapunov exponent. So you might heard Lyapunov exponent, which is in dynamics class, which is the measure of how particles get separate over time. So typical Lyapunov exponent has definition with a positive lambda t, but we're going to use a minus because the experiment-wise it's better to play this measure this Lyapunov exponent in the backward in time. So let me leave a minus time, that minus there. So this has been used in the many different cases. So one example is when jellyfish feeding the food in the water, what is the domain or what is the unstable or stable manifold this jellyfish would create. And another application people use is the search for the missing person. In this experiment, they did a mannequin. They released a mannequin in the ocean. And by knowing the ocean flow, you can predict where these mannequins go. So this can be used for search and rescue mission. So I'm trying to use this the analysis in our case, which is the leaf is vibrating. So as I mentioned, this is vortices or vortex dipole shedded from the edge of the leaf as the leaf is vibrating. So then there is a hyperbolic LCS, so Lagrangian coherent structure. Hyperbolic LCS is the region where you have a stable manifold and unstable manifold. So where the manifold is called the hyperbolic LCS. And where the vortices form is where we're gonna call it the elliptic LCS. So this is what people use in this community. So when there's the two particles separated, and then if you play it in time, you will get closer along the unstable manifold. So if you have a center point here, and then this flow is converging along the unstable manifold. So unstable manifold should have a positive, the Lyapunov exponent. Okay. And sorry, I'm just putting something here. And yeah, as I mentioned, the particles will accumulate along the unstable manifold. So that's what we expect to see in our experiment. So I will show you. So first, we calculate the elliptic LCS, which is we see the nice vortices form as the leaf is fluttering up and down. So this is quite intuitive. And the next image, we're going to show the Lyapunov exponent. So this red, the line is have a high value of the Lyapunov backward Lyapunov exponent, which means that is the unstable manifold is drawing up here. Okay. So as I showed this video earlier, so you're going to see nice vortices shedding, or the vortex dipoles are forming, and you're going to see most of the particles are accumulating on the edge of this kind of mushroom shape, which is where the unstable manifold is formed. So the people did more calculations. So how we're going to formulate the flux of the particles. So in this form, the omega is the vorticity, and S is shear. So this is or you can consider omega is the antisymmetric part of the shear strain, and this is the symmetric part of the shear strain. I will just explain more details. So first term is always positive. So because the air density is always lower than the particle density in our case. So when the omega is positive and when there's no shear happen, so then we expect this outflux, the value will be positive, which means the particles will be ejected from the coherent vortex. So this is a fancy way to explain the centrifugal force. It's nothing but the centrifugal force. If the particles are swirling around, the particles will be ejected outward. The other regime is, so when there's no vortices and when there's a shear happens, it's all along this unstable manifold. This is we have minus sign, you have plus sign, so then you're gonna get the minus sign, which means there's a incoming flux. So which means the particles will accumulate along this unstable manifold. So that's what it's showing here. So based on that, we ran the experiment with the particles. So those are the particles we tracked. And we're gonna calculate the Lyapunov exponent at the location of particles. So if these particles are moving to the region where have a higher Lyapunov exponent or unstable manifold, then this value will increase over time. So this is what we are showing in this study. So in this study, what we can show is where these particles are accumulate in the flow, which is where the unstable manifold form in the air. And then furthermore, as you keep generating this unstable manifold over time, repeatedly, then you're gonna spread this, you're gonna keep generating the unstable manifold from the tip of the leaf, and you're gonna keep pushing this unstable manifold away from the leaf. So that's why particles can be spread in the air. So this is the mechanism we show how spores can spread in the air. Frankly speaking, the agriculture engineers, they don't care about this kind of unstable manifold, but at least we can show that this is the if you have fluttering, or depending on the rigidity of the plant, you might have different the result of the spreading spores. So if you have a more rigid plant, then you're gonna spread the less spores. If you're more flexible, the plant species, then you can spread the spores out. So this is what I talked the earlier this week during the AMSI-ANZIAM meeting. I'm not going to go over any of this, but I want to give you one topic which is similar to the what I presented during the AMSI-ANZIAM meeting, which is bird diving. This is about the fox. Do you have snow here?
Not here.
Sometimes.
Sometimes.
Okay, so you
Like
know.
Australia.
Yes.
Yeah. When I give this talk in Saudi Arabia, I need to say there's imaginary materials called the snow. But you have some experience. Okay, good.
But
So yeah.
Sinno's sands are different, right? Because
Yeah,
they
yeah.
have sand there.
Oh, sand. Okay, so
In Saudi Arabia, probably not so necessary.
yeah, the desert fox. Yeah, fox sometimes behave to the sand too. Right. Yeah.
They have indoor skiing though, don't they? They have indoor skiing in Saudi
Indoor skiing. Yeah.
But there might be faults in
Yeah.
the ski.
Yeah, the Saudi Arabia, they spend like billions of dollars to host the Winter Olympics, right? So they plan to do something, making snow or something. I don't know. So this is the interesting animal behaviors, which is the diving behavior in the snow. So this is a video you can see. First, you're gonna see they move their head a little bit. So it's another interesting problem. They try to locate the source of sound where the prey is. So this is another project we are trying to do. The snow is porous material, as you know. So the sound could be delayed a little bit. So just we try to understand whether there's any kind of Snell's law through this interface or not. But there's something we are looking at too. Once they find the location of snow, and then if they know the depth of the snow, then they jump, leaps out of the ground, and then dives into snow. So this is overall trajectory in general. So we analyzed a couple of the videos, and we find out the speed of this diving, which is diving speed is around about like 4 meters per second, so which is a very high speed diving. And they can jump and then they reach around like 60 centimeters high. So snow is a very interesting material. It's a very complex material. So snow changes the density, few orders of magnitude. It's about 5 orders of magnitude. So the density 0 is doesn't make sense, but let's say 0.1 is the very like a loose snow. Then your Young's modulus, density change a few orders of magnitude. Also the Young's modulus change a few orders of magnitude. So Young's modulus start on the 10 to the 6. This is Young's modulus kind of rubber, like the elastic material. And if you have a go to the denser, the density, which is 1 is water on this region. So the 0.8, or you can consider this is ice. 0.8, you're gonna get the Young's modulus is about like 10 to the 10, which is kind of the Young's modulus of the metal. Right? It's almost ice, this region. So they change the Young's modulus significantly depending on density. Also, it changed the viscosity. So it can change starting from like 10 to the 4, it's like a honey, like a viscosity. It goes up to the 10 to the 9, which is the viscosity of the blacktop, the asphalt, what we are putting on the ground. So that's the asphalt is, in fact, is the liquid, not the solid. So that's why we need to replace the asphalt blacktop time to time. So when density is very low, it behaves like a fluid, so more viscous fluid, and almost less modulus. And then if you have a more dense snow, then it behaves like a solid. So you can change the behavior from fluid-like to the solid-like. You might have experienced this kind of behavior. So when you play the snowball, how you do it? How you make a snowball? You compress it, okay? And you throw it out. And if you hit, it hurts, right? This is solid, right? So when you compress it, then it behaves like a solid. However, when you shear it, when you plow the snow, you don't want to compress much. When you shear it, then it behaves like a fluid. So depending on how you treat your snow, you're gonna get a different response. So let's say whether animals can evolve in a way that to change the response of the snow. Okay, so that's the purpose of the study. So we scan many different animal, the fox species and other animals, the skull shape from the museum. And one thing we find out is all fox species has a very long snout compared to like puma or the bobcat, which has a short snout. You might have seen this kind of difference. The Canidae is the dog family. Dog used to have a longer snout. Felidae is the cat family. Cat used to have a short snout. Do you know why dog has a long snout and then why cat has a short snout? Sense of smell. Sense of smell? Okay, I think that's a good guess. But one of the explanation the biologists make is depend on their hunting behavior. Cats are solitary hunters, so they need to kill prey by themselves, which means they need to maximize the bite force. So if you have a shorter snout, then they can have the stronger bite force. The dogs, they're pack hunters. So they just move all together. So individual one doesn't have to kill prey, but the individual ones make a small damage on the prey, and eventually they're gonna catch the big prey. So that's why they don't have to maximize their bite force, but instead they have a long snout to make a little damage on prey. But anyway, the fox is the dog family, so they have a long snout. So then, if you have a long snout, so this is what biologists use a lot. It's a PCA analysis. So they got all morphological information. They put in the put in the PCA analysis, and then they can see where the certain skull shapes located in this kind of PCA axis. The PC1 is represent the long snout versus the short snout. All the skull species on the right is Canidae, which is a fox. Yeah, I'll show you. All species on the right is the cat family here. So what we try to do, we also try to make the skull shape by reducing the snout length arbitrarily and maintain the other area, the shape as much as what we are seeing in the fox. And this one is located in the start here, which belongs to close to the Felidae, which is a cat family. And what we did, we dropped that into water and we measure the force. And then you can see the force is 0 before the impact. At the moment of the impact, it starts to increase the force significantly. And once they submerge, then it keeps increasing the force because the hydrostatic force. So what happened to the snow? So we drop the skulls into snow. And then initially it has 0 force, it keep increasing, and then further up to the point D when they're fully submerged. And after that, they just steady because the snow is porous, so they don't hold any hydrostatic pressure in it. The other thing is we are very lucky to run this experiment thanks to global warming. We got a lot of the snows in this area, so hopefully we won't happen here. So and then we also this is something I did during AMSI-ANZIAM meeting. But we can understand what's impact force based on the shape. So impact force depends on the added mass change over the depth and the velocity square. And added mass here is depends on the radius of the object at the interface Q. When you have convex shape, the force will increase as square root of t, and then depends on the radius of curvature at the point and the lower point to the 3/2 power. So we're gonna look at what is the force what is the radius curvature of the fox. So we approximate this fox into the 2 spheroid, One is near the snout, the other is near the forehead here. And we can calculate what is the radius of curvature of those two locations. And then we can put this one in here, and then we can predict what is the force is going to be. So this is the original, the snout. We measure the force is increasing like this. And this is we are arbitrarily change the snout shape, and you're going to see the rapid increase of force. And theoretical model that I described can explain this kind of the force change over time quite accurately. And then what we are trying to emphasize is how much impact force they're going to experience. So we find out the flattened one, which is when the snout is short, then you will experience a huge force, twice force than the original shape, which means the fox evolved in a way that you have a sharp snout to reduce the impact force when they dive into snow. And then the longer snout helps to increase the shearing motion in the snow rather than compression. So that's why they're gonna reduce the impact force. If you compress as you penetrate, then you're gonna experience a huge resisting force because the snow will behave like a solid, not the fluid. So that is the what I want to explain, but later next week in the UWA, I will explain about the sound of hand clapping, which is this is an explanation using the Helmholtz resonator. So Helmholtz resonator, did you hear about Helmholtz resonator? It's something like a musical instrument. If you have the cello, then it creates the more low frequency sound. If you have violin, then you have a high frequency sound. Depending on the size of the cavity, you're gonna create the different frequency of sound. So in this study, what we are doing, if you make a clapping hands with the cup to cup, then you're gonna create the low frequency sound. If you make a small cavity using the palm to finger, you create the high frequency sound. So frequency of sound depends on the cavity of your hands. So depending on how you clap your hands, you can create the different frequency sound. This is what we're gonna explain in this paper. And the next week, also I think it's a Wednesday, University of Queensland, I will talk about how bat drinks water, which is an interesting behavior. It's a series of another drinking problem. So bat flies close to the water surface, and they take a sip of the water and fly up here. Inspired by this kind of bat drinking, we also look at the paper bat. So this is a paper airplane we designed in a certain way. I mean, there's a German guy, he is called by the paper airplane guy. So he has a book of paper airplane. One of the paper airplane he designed, this one is as you fly, you're gonna see this kind of you're gonna see the wings flapping passively, and also you're gonna see the pitching angle is changing. So due to the change, the pitching angle, it will make a flapping motion. So it's kind of passive flapping. So we're gonna explain this one next week too. And next week, the University of Queensland, another topic we're gonna talk about the snail-inspired robot. So we published this paper last year, which is how we're gonna we're gonna solve the thin film equation to understand the undulation underneath of the water, which is how the snails feed on the particles or floating particles in the air, in the water. And inspired by this, we try to make a robotic system to collect the microplastics in the ocean. So if you have a patch of the particle raft, and we can solve this particle raft using this mechanism. So this is something we are also working on right now. So as I mentioned, my goal today's seminar is to reduce your stress. So I will just prepare one more slide. Schadenfreude, did you hear about this? So this is a joyful feeling from watching someone fail. So my last slide. So this is a website of NSF, which is similar, the equivalent to the Australian Research Council. Each line is the proposal I submitted. Even though I pretend I'm very successful in front of you guys, but you can see below, decline, decline, return, decline, 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 decline. So I'm sure you have done better than me, and also you will do better than me. Yeah. All right, so hopefully you'll be happy by end of my talk. All right.
Thank you. Yeah.